So welcome to the OpenNEX seminar series. Today we have Xiaowei Jia from the University of Minnesota. Xiaowei is a PhD student with Vipin Kumar, and probably some of you may know Vipin is a famous computer science scientist from Minnesota that we've been working with for many years on data mining and machine learning area and satellite data. And Xiaowei is supposed to be the prodigy of Vipin, so Vipin highly recommends Xiaowei. And so Xiaowei actually came a few weeks ago and gave us a short seminar on some of the work he has been doing with satellite data. And I thought it was quite interesting, and all of you should really hear what he's doing. And that's why I kind of invited him back to give a formal seminar. And obviously we're going to record it and we'll be posting it on the web. But let him speak about some of the things that he has been doing, mainly in agriculture. Actually, a lot of interesting analysis of satellite data for agricultural monitoring and things like that.
Thank you, Robert. Yeah, so morning everyone. Very glad to be here. So yeah, I'm from University of Minnesota Computer Science Department. And today my topic is going to be science-guided applications of machine learning in the earth sciences. So we know that these days with the advancement brought of course by NASA, some other space agencies, now we have access to this kind of large-scale spatial-temporal remote sensing data set that cover very large regions and also have a regular frequency, temporal frequency. And we list a few very popular remote sensing or satellite imagery data sets. And we can see they are collected under different spatial and temporal resolutions, and most of them are globally available. So with access to such kind of large-scale satellite remote sensing spatial temporal data sets, this actually provides us huge opportunities to use machine learning and data mining techniques to monitor global changes and understand how these Earth systems works. And nowadays, we also know that the machine learning techniques is also developing very fast. From traditional support vector machine, SVM, to this deep learning, this is a very hot topic today. So if you go to this machine learning conference or data mining conference, you find everybody's working on deep learning these days. And even like people this day, they develop a lot of public libraries like TensorFlow, like PyTorch. They make these machine learning techniques very easy to use. And nowadays, most people can directly feed in the training data directly into a black box. So they don't even need to understand what the internal structure of the model. So they don't even need to customize this model according to the specific problems, but they can just directly feed in the data and train the model. So this is a so-called end-to-end training fashion. And this kind of technique actually have brought us huge success in a lot of commercial applications like recommender systems, like advertisement recommendation, and also search engine like social networks, all these kind of commercial applications. But at the same time, there's also bring us a lot of disappointing results, especially for some scientific domains. For example, the project of Google flu prediction. So there are several reasons for this. So one important reason is in a lot of scientific domain, there may not be a large amount of training data or label training data, so which are usually necessary for training a large-scale sophisticated deep learning model. And second, the system, a lot of scientific applications are quite complicated, so much more complicated than simply designing a recommender systems. So sometimes some unknown factors are not fully represented in this input features, so that's why they cannot be captured by a black box method. And also, if we simply train a black box method, sometimes the results provided by these models may not be physically meaningful. So we will talk about this later. But in this talk, we're going to cover two topics. The first one is we're going to propose some customized deep learning models to monitor global change using remote sensing data. And especially, we're going to cover two case studies. First, we want to map tree plantations in Southeast Asian countries. And the second, we want to monitor small-scale croplands. And then we will talk about how to build a hybrid model while combining these physical laws and the data science models. And specifically, we're going to apply this kind of technique in monitoring water temperature and water quality. So we start with a case study of mapping plantations. So we know this in Southeast Asian countries like Indonesia, Malaysia, the government really care about the expansion of plantations over time. So because the plantation is the main driver for deforestation in this region. So many farmers, they want to quickly clear the forest, so they use fires to clear the forest and convert them into plantations. But in this process, it usually comes with emission of large amount of carbon into the air, and also have some negative impacts to the water quality. So even if the government, we really want to monitor the dynamics of plantations, but so far the state-of-the-art or existing plantation products are still manually created. So basically they hire a group of domain experts and they visually check the satellite imagery like Landsat, and then they manually delineate the boundary of plantations. So because they are manually created, so it's very labor expensive. So all these state-of-the-art products are only available in certain years. So like this TP dataset is only available in 2014, and RSPO dataset is only available in 2000, 2005, and 2009. And our objective here is we want to use machine learning techniques to automatically generate yearly plantation maps. So think about it, if we have plantation maps at every year, then it would be very easy for us to analyze the dynamics of this expansion. But there are multiple challenges. First, if we want to train machine learning models, we need the multispectral features, but we also need the training labels. But now we don't have perfect training labels. We can only use these existing manually created maps as training labels. But because they are manually created, there are different kinds of problems. Like the TP dataset, it has very high recall, but it makes a lot of mistakes. So that means the precision is very low. And for RSPO dataset, it's very conservative, so it misses a lot of true plantations. And the second challenge is about the data heterogeneity, which means these plantations can look kind of different in different years and in different regions. So that means if we directly train a model in certain years and in certain regions, we cannot directly apply it to other regions or other years. And third challenge is the noise in remote sensing data. So we know that noise is always a problem for remote sensing data. And also, if we want to do a yearly classification, we want to use the multi-temporal data, which are collected under different days of a year to jointly do the classification. And on each day, there are usually multiple spectral bands. So we are going to use all these features to do the classification. And this problem is actually a typical predictive modeling problem, where we are given the features for each location, and we want to tell whether it's a plantation or not. And in our classification process, we find that there are more often, there are very frequent classification errors in certain years or in certain regions where there are more noise or more variability in these years. So one potential way to fix this classification error is to use the temporal transition pattern of the land covers. For example, in our study region, the Southeast Asia, we find a lot of forests are converted to plantations. But once they become plantations, they usually never come back to forest. So there are also some other similar kind of transition patterns between land covers over years. So we can potentially use this kind of transition pattern across years to fix the classification error in individual years. And that's why we built this recurrent structure to model the data dependencies across years. And the input to this model would be the multispectral data at each year. And at the same time, for each location, we collect the information from its spatial neighborhood, because we believe the spatial neighborhood can also affect the transition of land covers. So think about, like, for plantation cases, the new plantations are usually created around the existing plantations. So if we can look at the neighborhood of each location, we have better chance to know whether this location is going to be converted to plantations in next year or not. And when we do the prediction, because we mentioned there is some yearly difference, heterogeneity across years, so that means there may not exist a single classifier that can perform very well in different years. So what we do is, in prediction, we're going to dynamically update the classification model. So specifically, we're going to use an EM algorithm where we first do a one-step prediction, and then we collect the data from next year, and use this collected data from next year to update the model parameters. So actually, we create different copies of the classification model for the prediction in different years. And in this way, we can automatically, dynamically update this model or adapt this model to the new environment. And here we list some of our other innovations in this project, like how can we learn from multiple imperfect annotators. Like we don't have ground truth labels, but we have several sources of imperfect ground truths, how to learn jointly from them. and how can we aggregate the land cover classes and validate the results using random sampling method. And using such kind of techniques, we now build these annual plantation maps in Southeast Asia. You can see these red dots means the old plantations in 2001 or before 2001. And these green dots, you can see they keeps expanding over time. They are the new plantations that are created from 2002 to 2014. And you can see this year number keeps increasing until 2014, while these green dots also keep expanding over time. And according to our detection, we find the annual growth rate of plantation area is about 10%, which is really fast in this region. And now we're gonna combine this plantation product with the fire product to jointly analyze what's the relationship between forest fires and the plantation expansion. So in this central Kalimantan region, we show all the detected plantations in green color. And then we mark a subset of them into red color. So if we compare these two, we find a large number of them is marked in red color. And this red color means these plantations have burning scars in this period from 2001 to 2014. So actually, if we compare these two, we find over 60% of plantations have burning scars in this period. And then we mark another set of locations in blue color. And this blue color means these locations are not plantations, but they are also burned. And they have exactly the same burning date with nearby burned plantations. So it means the farmers, they want to use fires to clear the forest and convert them into plantations, but they cannot control the propagation of these fires. For example, in this region, they just want to create these small red patches to be plantations, but these fires keep propagating to this blue area and result in massive damage to the environment. The second topic is going to be we build an interpretable approach to map small-scale croplands. And it's also a classification problem. So for each year, we want to tell exactly what kind of crops are planted in each location. And we're still gonna do this for every year, and so we collect the multi-temporal data, or the data collected at multiple dates at this year for the classification. And we're gonna talk about our innovations on three aspects. First, how can we identify which period is more descriptive? And the second one is how can we combine the data from multiple scales, multiple different spatial and temporal resolutions to jointly do the classification. And the third one is how can we improve the model robustness against the noise. So as we mentioned, we use the multi-temporal or time series sequential data to do this classification at every year. And we find that for crops, for identifying crops, sometimes different crops cannot be easily distinguished with each other if we only focus on single snapshots. But rather, if you analyze the temporal growing patterns of different crop types, it would be very easy to distinguish or identify different crop types. So that's why we build a recurrent structure that model the dependencies across different days in each year to extract such kind of temporal growing patterns from for each type of crop. And at the same time, we also use the spatial context information because the spatial autocorrelation can help us improve the performance. But sometimes we find this temporal growing pattern only show up in certain part of a year or a part of the sequence. For example, in our case, if we want to identify a crop, we should put more focus on the period after the farmers plant the crop and before they harvest the crop. So actually, this can also provide us some interpretability to the prediction results, like from which period of a year can we better identify this class or this line cover. So we solve this problem using so this is actually a recurrent neural structure, and on top of that, we use an attention algorithm to find the period which has more descriptive information. And using such kind of technique, we apply this to identify corn versus soybean in southwestern Minnesota. And we find in 2016, the most descriptive period is from June 9th to July 11th. But we want to verify whether this detection is correct or not. So we take some sentinel image in June 23rd, 2016. And we find in this period, the corn and soybean can be very easily distinguished with each other. So that means our detection is meaningful. And also, this technique can be used to detect the shifting of planting time in different years. So we know that the farmers may plant this crop in different time in different years because the weather conditions change across years. So what we do is we train a model in 2016 and then test in 2015. So notice that we don't even need the training data from 2015 because our model can automatically find which period is more important along the sequence. So in this, so as we mentioned, there's some temporal heterogeneity across years. So that means we cannot directly apply it to another year, but we use some domain adaptation technique to fix this heterogeneity. And in these figures, these blue curves are the weights for different time steps in 2016, and this yellow curve are the weights for 2015. So if these weights are higher, that means these time steps are more important. And we see this yellow curve, this 2015 curve, starts to increase earlier than this blue curve. So that means the farmers probably, according to our detection, they probably they planted these crops earlier than 2016. And we want to verify that if that's correct. So we take some Landsat image in 2016 and 2015, and I think around 25th or 26th time steps. And we find this region in 2016 is only partially planted, but in 2015, it's showing much higher greenness level. So that means the farmers in 2015 probably they planted these crops earlier. So that's verify our detection. And also, if we can identify which period is more important, we also have potential to identify these crops earlier or before we collect the data from the entire year. So think about like when we do the classification, we use these ground truths from a USDA crop data layer. But they provide this, or they generate these crop maps in the next year. So they use all the data from previous to generate the yearly plantation, the yearly crop maps. But here, our method can provide some measure for the classification confidence. So once the method reach high enough confidence, we can stop here and only use the previous data to do the classification. So for example, if we only use data before 27th time step, we can also achieve a very high AUC score in classification. And also this technique can be used to do some real-time analysis for classification. Like here, we want to identify 3 different types of crops, corn, soybean, and sugar beet. And we monitor their classification confidence along the time, and we find that corn, this green line is for corn samples. They increase the confidence very fast at the early stage. So we take a sentinel image at this step to see, you can see that this yellow box, the yellow box is a corn croplands. They show much higher greenness level than the other 2 types of crops. So that's why they are gaining confidence early at this stage. So basically, the corn turns into green faster than the other 2 crop types. And we find, compared with corn and soybean, the sugar beets is gaining its confidence very slowly, but it's still increasing at the end of the year. So we take another image in October, which is this image, and then we find this red block, which is sugar beets. It still remains green color, but the other 2, corn and soybean, has already been harvested. So that basically verifies this classification confidence progression. And another interesting direction is how can we combine the data from different spatial and temporal resolution? Because we want to generate like this crop maps at higher resolution. So we don't want a lot of mixed pixels along the boundary. So we must map these crops at higher resolution data like Sentinel, like Landsat. But at the same time, this MODIS data or low resolution data, they are more frequently collected. So that means they can be useful in extracting or learning these temporal growing patterns to better identify these different crop types. And sometimes because they are more frequently collected, so they are less disturbed by the noise. And sometimes we generate this composite image under like every 8-day interval. And sometimes after this aggregation, they can have higher quality. So what we do is we first extract the temporal growing patterns from MODIS data. And then we feed these extracted patterns into the learning structure of the Sentinel data. So the learning structure of the Sentinel data is actually a generative model. And the extracted patterns, after these extracted patterns from MODIS is fed into this Sentinel data, so these patterns can guide the learning of the temporal patterns in Sentinel level. And then this method can also generate some missing or disturbed data at higher resolution. And finally, all these extracted patterns from Sentinel and from MODIS is going to be jointly used to do the classification. And we can see that after we combine this multi-scale data, the performance is going to be improved compared with simply using Sentinel for classification. And now I'm going to talk about the model robustness. So we know this noise is always a problem for remote sensing data, especially for high-resolution data. And nowadays, with this deep learning model or many sophisticated machine learning models, actually, even if they can achieve very high accuracy, like in all these applications like ImageNet, Contest, like this face recognition, NLP, and recommender systems, but actually, they are some previous work show that they are not very robust against noise. So the reason that they can achieve so high performance is because they use this multi-layer structure to extract all kinds of information or features that are helpful for the classification. So in our case, they not only use the crop phenology, but also they extract some other features from like the farmer's preference in arranging these croplands and the weather conditions, air quality. Even if we cannot see the difference in these features, but this machinery thought these features can still be useful in improving performance. Like maybe for corn croplands, the farmers may arrange this cropland in certain ways, but for soybean croplands, maybe the farmer did some other things. So this can also be potentially captured by this from the remote sensing data. But notice that these high performance features, even if they are helpful for improving the performance, but they are not very robust. So that means the difference in these features are not very significant across different classes. So that means if we add some noise to the features, the difference in these features are probably going to be gone. And the robust features, which is crop phenology, even if by only using these features may not give us very high classification accuracy, but it's very robust against the noise. So we did some theoretical analysis, and I'm gonna skip the details, but the result is that this error rate, after we add the noise, the error rate on these disturbed samples will be relevant to this dimension of hidden space. So basically, if we build a more sophisticated model, there are more chance that it's gonna be affected by the noise. And also, if we have more training data, if the density of the training data is higher, then this error rate will be lower. So the solution to this kind of problem, or to improve the robustness, so our solution is to use adversarial training on the time series data, or the sequential data, multi-temporal data. So adversarial training means if we add a perturbation on each sample, we hope after we add this perturbation or the noise, the loss function won't be changed too much. So it's like we first find a direction or adversarial direction which maximizes this loss. Then we want to minimize the loss along this worst case direction. So in this way, we hope to learn a very smooth classification boundary. And we can also extend this method to unlabeled data. So basically, we can simply replace this ground truth label by the conditional probability, which doesn't require any of the ground truth labels. And then we simply try to minimize the KL divergence between the conditional probability before and after we add this noise or perturbation. And this is for static data. And when we apply it on time series or multi-temporal data, we still want to focus on the discriminative period because that has more contribution to our classification. And for non-discriminative period, they usually contain a lot of variability, so it's less meaningful to add perturbation on those periods. And with such kind of technique, we show that the performance can indeed increase compared with the baseline method. And our lab actually has done a lot of other works in monitoring global change, like we capture all the forest fires in tropical regions, and we detect much more fires than the burn area product. And also, we create this global water monitoring system where you can access through this link, and we can click on any part of the world and see the change of water bodies. Like this part, it shows simultaneously water gains and water loss. And then we can verify in our system, we can verify this by this Google time-lapse video, where you can see that there are water exchange along different parts of the river. So it's a water meandering process. And now we want to go to the second topic, which is theory-guided data science. And I'll start with a static approach, which monitors the water temperature. And then we will extend this static approach to a dynamic system. So we know this in this traditional scientific domain, they frequently use this physics-based model. Basically, they want to model or capture the relationship from some input climate drivers to the target variable using their existing or their known physical laws. So they build this physical laws in physics-based models, and these models usually is quite inefficient in training because the cost function is usually non-differentiable. So they frequently use some grid search or some very time-consuming method to calibrate this model. And sometimes these physical laws used in building these models are not complete, so they ignore some other factors that may affect the output target variable. And the orthogonal direction is to use data science model. So this is more like a black box method where we directly feed in the data, and then they can automatically figure out the relation from input to the output. So the good thing about this model is it can be very efficient in training, and also it can achieve very high performance. But the bad thing is this method usually requires large amount of training data. And also the provided results from this model may not be very physically meaningful because it's not aware of the physical laws behind. So that's why we want to combine these two types of models to jointly use the physical laws and the learning capacity of data science models. To think about when we select the data science models, we usually prefer simpler models because the simpler models can be better generalized to different data sets, so they have lower variance. But if we choose a too simple model, usually they cannot give you a very high performance because they have a large bias. So this is a so-called bias and bias trade-off for data science models. But what can we benefit by bringing this physical knowledge? So we can potentially prune physically inconsistent solutions, and in this way, we can reduce the variance without likely affecting the bias. So that's the benefits why we want to combine these two. So the traditional data science model is more like a black box, and now after we incorporate this physical knowledge, we can open this black box to be a gray box. And we're going to show this in a specific example for monitoring water temperature. So we build a hybrid model by first, we use the outputs from physical models as input to training a data science model or like a neural network. So the intuition is that even if this output from physical models, they are not 100% accurate, but at least they can provide us some insights about the physical laws used in building these physical models. And this neural network then, they can automatically figure out the gap between these physical model outputs and the true observations, given these input climate drivers. And this method can even be applied to unlabeled data because as long as we have input drivers, we can generate a simulated output from physical models. And we know that in this example, in the water temperature modeling, there's a relationship for the density of water. So the density of water always going to the bottom of the water body. So the density of water is always have a higher depth. And there's also a correspondence between the density and temperature. So we can use this kind of relation, and we can first transform the predicted temperature into density, and then apply these constraints on the output. So basically, that's how we define our cost function. So this is the original cost function of the neural networks after we combine with these the model from the physical, the output from physical model, and then we add a regularizer on the physical laws in this example. And after we use this technique, so we want to show a result on a certain date, and here this diamond shape are the true observations for density on for different depths, and we can see it should monotonically increase along the depths. But if we only train a pure data science neural network model, you can see the result going back and forth, so it violates this density relationship. And if we build this hybrid model, physics-guided neural network, then you can see this blue curve achieve both higher accuracy and it also conforms to this density relationship. And if we measure the performance in terms of RMSE and this violation of this depth relationship, then we can see compared with the physical model, this hybrid model can significantly reduce the classification error And compared with data science models, it can significantly reduce the violation of this density relationship. And now we're going to extend this static model to a dynamic model, because in real-world system, there are usually a lot of data dependencies across space and across time, like the energy can transfer over time and across different depths, and also the volume can change, and there's nutrient accumulation over time. So this can only be captured if we build a model to model their dependencies across depths and across time in the lake structure. So that's how we build this two-dimensional recurrent structure. And this also makes it possible to more naturally incorporate these physical laws. Like along the depths, we can incorporate that density relationship like we just mentioned, and along the time dimension, we can incorporate the energy conservation. So we build this hybrid model, this dynamic model in 3 steps. The first step is similar to the static model, where we use the output from physical models as input to this data science model. And the second step is we use the physical model outputs to feed in some missing observations. So the intuition is that the training of this recurrent structure usually require a large amount of training data, or very frequent training data to learn these temporal dependencies. But this is usually not available for real-world scientific systems. So that's why we use the physical model to generate some simulated outputs in those missing dates. And we define our cost function in 2 parts. The first part is defined simply on the true observations, and the second part is defined on the simulated outputs. And there's a hyperparameter lambda to control the balance between these 2 parts. And the third step is we're going to incorporate some additional constraints, or we're going to build some hybrid structure in these recurrent neural networks to capture more physical laws. So we first show the performance in terms of RMSE for different depths. So this is for the physical model, general lake model, and this is for the hybrid model and data science model. And we find the error mostly occur in the middle part of the water. So this is the depth, and this is the error. And same for the data science models. But data science model actually achieve much lower error than this physical model. You can see the scale of these 2 figures are different. And the main reason for this is the middle part of the water usually have a higher variability or more water exchange. So if we take a closer look at this middle part of the water, we find that this prediction, these lines, this curve in magenta color are the predictions by our hybrid model. And these blue spikes are the true observation. And you can see this curve, this in magenta color actually matches these blue spikes much better than other curves. And this green line is the outputs from the physical models. So you can see at this depth, the physical model almost meaningless. And this orange colored curve is the prediction by the pure data science model. So you can see it has a very large bias at these depths. So the reason is that this pure data science model, it just totally ignores the dependencies or the relation across different depths. Another important concept is energy conservation. So in our case, there's a lake energy budget, which basically measures the balance between incoming energy and outgoing energy. And if we have more energy gain than energy loss, the temperature is going to increase, and otherwise it's going to decrease. So it's very easy to understand. And there are a set of differential equations to define this process. And our hybrid model we built should be aware of such kind of energy conservation over time. And we're going to incorporate this kind of like differential system into our recurrent structure. So after we incorporate this kind of knowledge, this energy conservation over time, we can find this method can significantly reduce the error at different depths, especially for the lower part of the water. And sometimes these domain scientists, they are more interested in some other measures that can be very helpful for their study, like the position of thermocline, which means a layer in the water body where the temperature changes more fast than other layers. So the position of this thermocline can be very helpful for the study of lake stratification and also for the energy propagation across different depths. And now we show this predicted temperature in these heat maps where this red color means higher temperature and the blue color means lower temperature. And these gray dots are the detected position of thermocline according to our predicted temperatures. And after we incorporate this energy conservation, we find that we get a very smooth profile of these thermal compositions. So compared with the ones without using energy conservation. And this actually makes more sense for this domain. And now I want to conclude this work. So first, we show that the big data or machine learning techniques have huge promise for us to better understand the Earth system. And second, we show that this domain theory can be combined into a hybrid model with data science models to jointly do this discovery in the scientific domains. And third, we believe that there's also huge potential in combining this remote sensing data with this theory-guided data science framework. So the reason is, in many scientific applications, even for the input climate drivers, they are not very frequently available, or they may not be able to capture all the factors that will affect the output or the target variable. But the remote sensing data, they are collected or available at large scale at every location and at a very high temporal frequency. So potentially, like in crop yield prediction, we can use remote sensing data to model or capture this accumulation of greenness level over dates. And also, we can combine that with some soil analysis and other physical laws to jointly model the growing patterns or growing process of crops and jointly do the crop yield prediction. And also, we can use remote sensing data potentially in modeling this or monitoring the water quality or water clarity. And finally, all this proposed method, we believe they have a general applicability across different applications like finance, like healthcare, or even some commercial applications. And thank you for attending this talk. And